nanohub.org.
All right, well, I guess we'll get started. Get me a... Okay, great. Okay, so today we're going to, so previously we looked at static force distance curves where the cantilever was quasi-statically approaching the sample. We weren't driving the cantilever to make it oscillate. So today we're going to look at what we call dynamic approach curves, and that basically means that the cantilever is vibrating while we approach the sample. Okay? And there's two simulation tools which are relevant to that experiment in VEDA. Okay, so first the caveat here is that we're basically going to be looking at ambient and ultra-high vacuum conditions for this. And what we mean by that is we're going to model the cantilever, which is a continuous structure. It has properties like elastic modulus and area moment of inertia, damping coefficients and length and stuff. We have a continuous structure, but we're going to be modeling that as a single degree of freedom point mass oscillator. And this is a pretty good approximation, particularly in ambient conditions for most conventional applications. There are some advanced applications where maybe we drive the cantilever off resonance, or we have bimodal excitation, multi-frequency, some advanced techniques, but conventionally operating near the bandwidth of the first resonance in ambient, the single degree of freedom approximation is pretty good, and that's basically what we're going to be doing today. And it makes the program a little bit simpler if we can make those assumptions. Secondly, so the point mass oscillator has a stiffness K, a damping coefficient C, and a mass M. But typically in the experimental observables, we write those in terms of the quality factor, which is given by this expression here, and the mass we'll write in terms of the natural frequency, omega 0, of the cantilever oscillating freely in space. Okay. Finally, the sample I've indicated here in red, and that's to represent repulsive contact forces when we contact the sample. But I should also note that in a non-contact regime, we're going to feel the effects of non-contact long-range interaction forces. Okay, so the first thing that we would do typically if we, before we started to do it, ultimately we want to get to take an image in dynamic AFM. So let's assume that's our objective. The very first thing you would do is some sort of tuning curve to identify where the resonance is. So typically a manufacturer will specify a resonance frequency, maybe plus or minus 5% or so, maybe 10% of the cantilever resonance. But in ambient environments, the quality factor is on the order of 100, which means the bandwidth of the resonance is 1 part per 100. In addition to that, we need to be pretty close to the middle of the resonance bandwidth. So we're talking about 1 part per 1,000, 1 part per 10,000 that we need to know the resonance frequency. So it's important to do basically a tuning curve to figure out exactly where the resonance frequency is. So in this example, we're going to use the same cantilever that we've been using before, which is actually a fairly soft cantilever for ambient environments, but it has a stiffness, so the fundamental mode is 0.87. Quality factor here is 33. I know the resonance frequency. I'm just doing this demonstration to show you what the tuning curve might look like in an experiment. And we're going to start at a drive frequency of 20 and go up to 100, and that's going to help us sweep over the resonance to identify where it is. And finally, note this: I put in a z separation of 35 nanometers. So we're far away from the sample compared to the unconstrained amplitude value of 10 nanometers. And secondly, we're going to use the Hertz contact model here, and that means when we're at the z of 35 nanometers and amplitude of 10 nanometers, we're not feeling any effects. In the model, there's 0 effects of tip sample interaction. In reality, it's always some very small but negligible quantity. And this is the conditions that we want to be at to do the tuning curve to determine the unperturbed resonance of the cantilever freely oscillating. So we do this, we get this result, we sweep over the frequencies, and we get a Lorentzian response for the amplitude. It looks something like this. I'm going over this, I don't know how familiar you guys are with vibrations, but it should look pretty familiar. And then the phase response also for a single degree of freedom oscillator. Phase goes through 90 at the resonance frequency. Finally, I would note that sort of our motivation for this tool, this isn't really a very exciting simulation if you think about it. You're just sweeping the cantilever by itself. It's not interacting with the sample. We developed this tool in our group because we want to study the nonlinear responses when we approach the sample closer and we're actually tapping on this, and you'll see bending of the resonances and you'll see multiple oscillation states and things like that. It's not quite as relevant an experiment for the experimentalists, though. Just doing the tuning curve to find the natural frequency is what's more commonly done from an experimental point of view. Okay? All right, so were you guys able to do this simulation? What's up? Okay. Yes?
Could you comment on the sign of the phase?
Yes. Okay, so oftentimes people are a little bit loose in their terminology with the phase. It can either be what we call phase lead or phase lag. And that basically means if it's phase lag, it's a difference of a sign. And if it's phase lag, it should be 90 at resonance. And if it's phase lead, it should be minus 90 at resonance. And that's the distinction. They're just plus or minus of each other. That's the only thing. Also, in the experiment, when you do this curve, probably you're going to have a delay because of the response of the dither piezo you apply the voltage to, and possibly some electronics, some phase lag in the electronics. But you can calibrate that knowing that at the peak, around the peak, it should be at 90 degrees. So you probably shift the phase when you do the tuning curve. Okay. So we're good on this? Okay. So now onto what's really a much more relevant simulation for the experimentalist point of view is the dynamic approach curves. And we're going to do this today in amplitude modulation AFM, or the experiment which is relevant to amplitude modulation AFM. And that means we excite the cantilever at its resonance frequency we found from the tuning curve, and we approach the sample. And at this point, there's no feedback regulation on any of the outputs. If we do this in frequency modulation or some other modes, there are actually nested feedback loops that are there. But here, the cantilever is not subjected to any feedback regulation, and it just is approaching the sample and interacting with the sample. So again, our sample is indicated here. Red is to represent contact repulsive forces, and blue for long-range forces. Okay, and so initially we'll excite the cantilever. We're far removed from the surface of the sample, and here the cantilever attains a amplitude of A0, which we refer to as the unconstrained amplitude. The experimental observables, which are very important, are basically the base displacement Z, although we don't know the datum of Z, but it's not important. The unconstrained amplitude A0, and what we call the unconstrained phase, if you will, but that should be 90 degrees. Okay? And we approach the sample by reducing Z. And at this point, we'll first encounter attractive forces where the net interaction is attractive, and the amplitude will become reduced from its original unconstrained value. So we call that the reduced amplitude, and just the phase of the oscillation at that point. approaching the sample further, we'll get into the repulsive regime where the net interaction is repulsive, and that's so we name that the repulsive regime. Okay. Okay, so if you'll go to the amplitude modulation approach curves basic tool from the drop-down menu. Okay, so we'll get to input page for the operating conditions in the cantilever, which looks very similar to the sweep tool, but here we're going to specify, again, like in the static force distance curves tool, we're specifying the Z range and initial and final Z separations. And this first example is going to be very basic. Let's choose Hertz contact forces, and the default values here would be fine, but just note that Hertz contact, there's no non-contact forces, just the repulsive forces encountered during contact. Finally, there's simulation parameters for this tool, and the default values again are fine here, except let's choose to include time histories, and that'll be important later. And what this is going to do is, generally the outputs are amplitude and phase, which are the experimental observables, but here we're just going to take a small sample of the deflection waveform, the tip sample interaction forces that are encountered at these amplitude ratios. And I should note that, so an important distinction in dynamic AFM is our observables are amplitudes, the phase, and the Z displacement. We're recording the deflection wave, or we're measuring the deflection waveform, but this probably isn't recorded during the experiment because of the amount of data that would be. Typically that's thrown out. But more importantly, we're not directly measuring the tip sample interaction forces. Okay, so that's an important concept that we'll go over. Okay, so let's go ahead and simulate this. The first result that comes up after about a minute is going to be the amplitude. Here we call it A1 of the primary harmonic of the oscillation, and this is going to be plotted versus the Z distance, the displacement of the base. Okay? And for the simple Hertz contact model, which only includes repulsive forces, this curve is pretty plain. Basically, we approach, nothing happens until we hit the sample and it starts to decrease almost looks linear, although it isn't. Okay. The second result I'll discuss is, here is the phase lag, actually the oscillation. And here we approach, again, it's at its initial value of about 90 degrees. And then it starts to, because of the detuning from the interaction, it starts to shift. Okay? Okay, so next I'll ask you guys a question, and so one of the reasons why we do the dynamic approach curve simulation is we want to pick out favorable conditions to take the image, right? So we're going to pick things like operating amplitudes and set point ratios, and those are actually going to be what we're going to use when you turn on the feedback, scan over the sample to create an image in amplitude modulation. So, and one thing we might be particularly concerned about is how much force we're exerting on the sample, because the image we create is ultimately going to be related to the forces, and we want to have some measure of that. So the question for you guys is, what amplitude ratio are the peak forces maximized from the simulation? Okay. So it'll take a minute to you don't have to run a new simulation, but take a minute to pick through the output plots, familiarize yourself with the outputs from this. There are several other outputs besides amplitude and phase. So take a minute to browse through those and see if you can answer this question. Okay, and so I point out that initially in the simulation parameters we've chosen on that page to plot all these quantities versus the z displacement. Okay, and this is maybe convenient because it looks like what your experiment is going to look like when you do the experiment. Of course, you're not going to measure peak force directly, but if you did amplitude and phase, the first curve you're going to record with the instrument is probably going to be those things plotted versus the z displacement of the piezo. Okay, but ultimately when we go to take an image, you're going to be interested in how these quantities vary with the set point ratio, because that's what you're going to be controlling in the feedback loop. So we have our choice over set point ratios, but we're not directly controlling the z distance. It's actuated through that feedback regulator on amplitude. So we notice that this happens at around z equals 0.93 nanometers, and if we went back to amplitude, or 0.5 nanometers, and we figure out that that's around 0.5 nanometers, which is about a 50% amplitude ratio. But another way to do this in the simulation, actually, is if you go back to the simulation parameters, there's an option here to choose the x-axis variable, and if you select amplitude ratio, then you can redo the simulation, and here it's going to plot peak force versus the amplitude ratio, and then we can directly see in that curve. And it's a nice thing to do if you're comparing what will happen at different regions of the sample or different simulations and so forth, to plot those things versus amplitude ratio. Okay. Oh, what happened to my question? Okay, so let's do a second example here. Let's keep that simulation active, or actually, if you haven't, clear the simulation and redo it for amplitude ratio. And while you're doing that, we're going to want to run a second simulation subsequently. And here we're going to go to tip sample interaction properties, and we're going to make this interaction non-conservative. So what we do is we add a viscoelastic component of the interaction, and that's modeled by a Kelvin-Voigt interaction. And so if you scroll down to the portion of the panel which talks about non-conservative forces, and you can include a viscoelastic force modeled by Kelvin-Voigt, and enter in a pretty big value of 1,000 here. Also scroll up on that page and make sure the Young's modulus is unity. It's one GPa. I don't remember the default value for that. Okay. So I'll just do this here. Okay. Okay. So we're on the same page? Okay, so the question I have for you is, if we are choosing a set point ratio and we're interested in a phase contrast image between, which will occur from varying degrees of non-conservative interactions with the sample, we want to pick possibly a amplitude ratio where we can maximize that contrast, which happens between maybe a viscous region of the sample and a more conservative region of the sample. So the question is, what type of amplitude ratio should we choose if we're interested in maximizing the contrast between those two regions of the sample in the phase contrast image, in the phase image? Okay, so if you ran these two simulations, so for two separate approach curves, and we can choose to select to display all, and go to the phase, first harmonic phase versus amplitude ratio. Okay? And what this is showing us is the deviation between these two lines. The first simulation was for a conservative interaction, and the phase will follow the arc sine of the amplitude ratio. And then for the dissipative interactions, we'll start to see a deviation, a shift upwards from that portion of the curve. And if we choose a given set point ratio for the image, maybe 0.8 or 0.6, the deviation between those two lines is basically what contrast will be observed while you're scanning over the sample. Of course, there'll be some transients as the controller is adjusting different regions of the sample, but basically the deviation between these two lines is what's theoretically expected when you take the image of a sample which had these two different regions. Okay? You notice that basically as we tap harder and harder on the sample, reducing the amplitude ratio, basically the deviation between these two lines grows. And essentially, if you're interested in phase contrast imaging or material property contrast, basically you want to tap pretty hard on the sample. That is what that's telling you. Although if you're concerned with what that's going to do to your image resolution, or if it's going to damage your sample, then you have to sort of pick a higher set point ratio, which would be where you're more gently tapping on the sample. So it's a sort of a trade-off. You can't have them both, but that's so. If we're imaging a polymer and we're not too worried about damaging it, we might pick a lower set point to get a better phase contrast. If you're imaging a soft, fragile biological sample, you probably want to pick a higher set point ratio to avoid tapping on it. But if we're stuck with the phase contrast image won't be as great at that point. Okay. So let's go into example 2 here. Okay, and so actually we want to change the tip sample interaction model from Hertz to DMT. Okay, and the important distinction between those two is that the DMT has an attractive van der Waals component. That's very important to the dynamics. We can now have attractive and repulsive regimes of oscillation. Before that didn't happen in the Hertz contact model. Okay. Also, so I skipped over this before, but let's go to the time histories and let's select 0.8, 0.3, and 0.1 for the amplitude ratios where we record time histories. Okay. Finally, I sort of did this backwards, but let's go to the operating conditions and cantilever properties. We're going to use the same cantilever that we've been using, but here we're going to want to run 2 simulations. The first is going to be approaching the sample, so we'll choose to specify the Z range. And the first is going to be approaching the sample from initially at 15 nanometers down to 0. And then our second simulation is going to be inverting those 2 parameters. It's going to be a retraction curve where we start at 0 and retract from the sample. So those 2 simulations might take you a couple minutes to run. Okay. I think everybody has something either correct or very close to being right, so good enough for government work, right? Okay.
How do you know when it's close to being right and when it's right?
Qualitatively, I've seen the basic features I was looking for. Jumps in attractive pulsive regime and a snap-in. Some of them look like they're happening at slightly different amplitude ratios, so I think somewhere somebody has a parameter slightly different, but I think it's okay. Or do you have a more general question about comparing to experimental?
When you use this software, how do you know? How can you have any confidence that what you get is what you're actually trying to simulate?
I see.
How do you think about that?
Right, so in terms of the modeling, I think one of the bigger uncertainties in the modeling comes from the tip-sample interaction, right? Cantilever model is pretty reasonable. Everything else, there's lock-ins and all kinds of things that are pretty good. So if you started with doing a force distance curve and use the force distance curve tool, and you tried to get a model that matched pretty well to your experimental data, then I think you're in pretty good shape. The one other big deviation we see a lot in the experiments is that the piezo isn't doing exactly what we told it to. So the Z piezo, which we're approaching with. If you have an open loop piezo, you're sort of at the mercy of the piezo behaving nicely. It can have hysteresis loops because of the voltage applied, or it can drift because you tried to approach too fast and the piezo is creeping as you're expanding. One thing I've noticed there is so if you eliminate the Z piezo from the plots you're looking at, if you plot versus amplitude ratio, so phase versus amplitude ratio suddenly becomes much more reproducible. For instance, if we were trying to match experimental data to the simulation. And that's because I don't really trust the Z piezo measurement so much. It's when we're sweeping over large ranges. It's better when we're imaging and we're having very small changes in the Z position, but when we're sweeping over 100 nanometers or something very quickly. But if you have a closed loop Z piezo, that's much better. Under that, if you do the static force distance curve and you do the simulation and you finagle the parameters a little bit, then you should feel pretty good about that part of it. So, okay. Okay, so we did these two simulations. One is approaching the sample, and then the other one is retracting from the sample, where the Z initial is at 0 and Z final is at 15 nanometers. And the first result that comes up here is the amplitude versus Z distance. So even though we plot versus amplitude ratio, of course the one plot that comes up versus Z is amplitude, because we don't like plotting 45-degree lines. So the first plot is amplitude versus Z distance, and you can see that it's hysteretic on approach and retract. And on approach, we follow this lower branch, and then suddenly around Z equal, 2 nanometers, there's a jump up to a common branch, and then we approach, so that's a gray one where we're approaching, and then eventually we touch the sample and basically the amplitude is gone. And then on retraction, it stays stuck on the sample until some point where it pops off. So that's a snap-in phenomenon that you've seen in the quasi-static approach curves or the force distance curves. That's the same phenomenon, but except the amplitude is reducing. It's a little bit more complicated now because the tip is vibrating around a little bit, but basically this is the same phenomenon. So there's a bistable region for the equilibrium of the tip stuck onto the sample and popped off of the sample. But in addition, there's the second bistable regime, and this is attractive and repulsive. Has to do with attractive and repulsive regimes of oscillation. So in one case, we approach the sample, we feel the attractive forces, the van der Waals forces, they're reducing the amplitude, and then at the same set point on retraction, at the same Z distance, we're actually tapping on the sample, just simply based on initial conditions, and because this is a nonlinear system, we can't assume too much that it'll behave nicely, basically. Okay. And So address one other thing. When we plot these things versus amplitude ratio, what happens is when we're transitioning from one branch to another, there are transients, okay? So when we plot these curves, you'll see like a stray point here and there, and that has to do with the fact that we're simulating versus the Z approach. We're monitoring amplitude, and as we jump from one branch to another, the cantilever is transitioning from those branches. There's some transients involved in between. So be careful with your mouse over tool when you look at these. And if you want to know if it's a legitimate sort of segment of the curve or if it's just a straight point, you'll be able to see if it's a single point or if it's a whole family of curves, of points or not. So probably we're going to change this to plot single points instead of plotting connected points to make that more apparent. But for the time being, that's the case. Okay, and so the way that we name attractive and repulsive regimes of oscillation is by the net interaction force. So we might graze the sample and encounter repulsive forces or not, but they're named by the fact that the net interaction or the time average interaction will either be attractive or repulsive. So in this plot versus, which is mean forces versus amplitude ratio, you'll see that for this large region in the middle where it's bistable, the two different, the approach and the retraction have either a positive mean force or a negative mean force. So that means the regime of oscillation is either attractive or repulsive based on the sign of the mean force. Okay? And one way, so technically you can measure mean force and amplitude modulation AFM, but you're much better off looking at the phase of the oscillation. So mean force is probably pretty small, and it's not very easy to measure. It's not always very easy to measure mean deflections with high resolution. So what you would look at here is actually the phase of the oscillation. And what will happen is when we're in the attractive regime on approach, the phase lag will actually increase above 90. And when we start tapping on the sample in the repulsive regime, the phase will be below 90. So that can be your test experimentally determine which regime of oscillation you're in. Okay, since we don't measure the interaction forces directly. Okay. Okay, so from here, you guys don't need to run any new simulations. Just sift through the results of this simulation, and I have these 3 questions for you to try to answer. One is, what amplitude ratio should we choose to ensure that we're in a monostable regime of oscillation? So what can happen is if you're imaging and you're in a bistable regime, is that you can transition back and forth between the two regimes, and that causes imaging artifacts, basically. And the second one is, the follow-up question is, what kind of errors and artifacts in topography can be encountered by imaging in a bistable regime? And then third, what can we do to reduce the bistable regime? And, okay. So let's assume that we're stuck with a cantilever in the sample we have, and what can we do to try to make the bistable regime smaller? Okay. So let's go on to try to answer these questions. Actually, first I'm going to run my second simulation. Okay, so while that's running, we'll go ahead and discuss the results. So, what amplitude ratio should we pick if we want to be in a monostable regime? Okay, so if you go to the amplitude as plotted versus z distance, you'll notice that these two curves are on top of each other, and small sections of this, right? So first of all, for amplitude ratio is approximately on this interval 0.2 to 0.3, we're in a monostable regime where the two curves are on top of each other. And when the amplitude ratio is above about 0.95, we're also in a monostable regime. Here it's actually, the lower one is the repulsive regime, or monostable repulsive regime, and the high amplitude ratio is monostable attractive regime, okay? So probably in tapping mode, you want to pick the repulsive regime, and that's because actually the resolution of the forces themselves are greater in the repulsive regime. You think if you take an image and you're basically making a mapping of interaction forces, if you're using long-range forces, then they're coming from a larger region of the sample. So when we're tapping on the repulsive forces, we probably get better resolution image. Okay. The second is, so what can happen if we image in the bistable region? So I mentioned before, if it's bistable, which branch we're on depends on whether the initial conditions, right? So when we approached the sample, we stayed on the attractive branch. The amplitude got smaller because of the attractive forces. But when we got too close and we touched the sample, we went to the repulsive. And then on the retraction curve, we actually stayed on the repulsive oscillation branch. So what can happen is we're imaging over the sample and we're adjusting the Z piezo with the amplitude feedback. If we encounter bumps and irregularities of the sample, there's always a possibility for you to go from one oscillation state to the other, right? Because we're changing sort of initial conditions. We might bump into the sample a little bit harder and so forth. So basically what can happen is, in this case, if we chose the set point ratio at, say, about 80%, you can get a transition back and forth between those two stable oscillation states, and that can be sort of an imaging artifact. Here it's about half a nanometer can happen from that, which is clearly undesirable. Okay? And the final question is, what can we do to reduce the bistable regime, right? And if we're stuck with the cantilever we have to take an image of the sample that we have. We can't change anything there, but we can do is basically increase the amplitude, right? So you notice in this example, there's a very large bistable regime. It's kind of a pretty precarious scenario that we have to image at this very low set point of maybe 0.25, or we have to compromise the resolution and image at a very high set point. So it's a pretty undesirable scenario to try to take an image under. And if we get any closer, we have a bistable equilibrium where this tip can snap onto the sample, and any hopes of taking a reasonable image are gone at that point. But what we can do is we can drive the cantilever with a larger amplitude, okay? And if you think about this, it's basically you're putting more energy into the oscillation of the cantilever, and it's going to be harder for the same attractive forces to reduce the amplitude. So what will happen is and I left that simulation, so we'll just do it here in this case. We'll do it live. So let's say we increase this to 25 nanometers. Or let's just do double, 20 nanometers. We're going to approach now from 25 nanometers. We'll do this simulation. Okay. So you plot all, what you'll see is basically the region of this bistable region here shrank a great deal, basically, just by doubling the amplitude. So now we have a much larger range of set points that we can image with, and that ensure that we're in the repulsive monostable region, which is generally what you want to do in tapping mode, or in amplitude modulation AFM imaging. Okay. Finally, since we have a little bit of time, I wanted to show you this one result, so I'll redo this simulation. So you notice we picked, I didn't show you anything about time histories yet, but we chose to include 3 time histories, and we're taking them at samples of 0.8, 0.3, and 0.1. And we're going to do 6 oscillation cycles here. Okay. So let's look at deflection and force history. At 0.8, what you see is the tip is oscillating, and it's interacting with the van der Waals forces closest to the bottom of the oscillation cycle. And here, so the peak forces are, about minus 1.5 nanonewtons. This is what the oscillation looks like at set point ratio. This is what the forces in the waveform look like. If we go down to 0.3, somewhat an interesting result here. So you notice that still we're in the attractive regime, and we haven't touched any repulsive forces yet. But you'll see that the tip sample interaction forces in green look somewhat irregular, right? So they're not repeating exactly every cycle. And actually, because it's a nonlinear system, it doesn't even ensure that you get periodic oscillations, right? They might be, or that they repeat every drive cycle. They might repeat every other drive cycle. So this is what we call a period 2 oscillation, where every other drive cycle, the oscillation comes back to its original point. And then finally, if we go down to 0.1, or A0, here is where we're actually tapping on the sample. You can see these pretty characteristic looking tip sample interaction waveform for tapping mode AFM. It has and DMT contact. But occasionally, under experimental conditions, we might have a hysteretic force, in which case one of the peak attractive forces will look a little bit different from the other one because of some hysteresis and adhesion and so forth. But this is characteristic of what we will see in most AFM experiments in tapping mode AFM if we were able to look at the tip sample interaction waveform. Okay? I think that's, yeah, we're a few minutes early, but if there's you guys have any questions maybe about? You didn't get 0.8. Did you break it? So that one's it's a little bit tricky sometimes. Did you do the retraction curve or the approach curve? It didn't come out. Yeah, it's not the best logic that decides when to spit those curves out, but so just breathe on it or tilt your computer a little bit and it'll come out. Possibly, maybe you jumped in between the two at 0.8, or if you have slightly different numbers in or something. Yeah, occasionally it doesn't like to give you the waveform you asked for because. Yeah, but maybe it didn't. Or sometimes you'll get errors because you won't reach the set point that you asked for. Other times there's a jump over it or something like that, and Yeah, so, but occasionally I think it just makes a mistake. I don't know. But, anyway. Narendra. Yeah.
For the bistable regions and if we avoid the bistable regions, how will be the phase behavior?
Okay, so initially what you'll see usually, maybe I'll draw it on the board because it'll look a little bit. What will the phase? The question is, what will the phase look like if we avoid bistable regions? And so if we're plotting this, the phase lag, phi versus amplitude ratio. And again, we're going to start at the unconstrained value, which you get a whole lot of points right here. Initially it'll increase in the attractive regime, and then what happens is there's a jump at this point, at some point where we touch the repulsive forces too much, and we jump off this attractive regime oscillations down to a repulsive regime, right? And then on retraction, let's say it's in dashed line, will follow something like this, okay? So in the bistable regime, we'll have two branches which look sort of mirrored from each other, but eventually they'll join in the repulsive regime. This will have to be less than 90 degrees, and both curves from the approach and retraction should be very close to each other. It won't be perfect because it's an experiment, but in the simulation they'll be on top of each other basically. Almost exactly. Okay. And the fact that it's less than 90 indicates it's repulsive, it's attractive, it's greater than 90. But yeah, basically you're wanting to avoid regions where the curves have hysteresis in them. So indicating that they could be at two different oscillation states in that region. Okay.